I don't know your current age, so let me assume you're currently X years old. Let's consider your age when you die. Now, I don't know your current age, and neither of us know when you'll die. So let's use variable t to represent the time from now until you die. So your age at death is X plus t. Actuaries are very interested in modeling how long people have to live. So let's make t a random variable. Recall we use capital letters for random variables. Thus, capital T is your time until death random variable. Your age at death now becomes X plus t. It's quite likely that your time until death random variable t is different than mine, since you're likely younger than me. It would make sense to distinguish your time until death random variable by which age we start. We distinguish by writing a subscript after the t for the beginning age. Since your age X, your time until death random variable is t sub x. Because we can die at any time, t sub x is your continuous random variable for the time until your death. In a sense, t sub x is your future lifetime, given you're currently age x. Because we often refer to ages, minimize notation by enclosing age within parentheses. Parentheses indicates age, so x within parentheses refers to age x. 20 within parentheses refers to age 20. When we use the notation 20 within parentheses, or t sub 20, we assume age 20 is alive at age 20. In summary, we assume you're currently alive at age x. The number of years you have to live is a continuous random variable t sub x. Your age at death is your current age plus the time from now yet to live, which is x plus capital T sub x. Since the time until your death is a random variable, we can use all the probability tools from the probability exam. Let's start by first reviewing t's survival function, and then the survival function's complement, the CDF. Let's write a probability statement you survive at least 10 more years, given you're currently age x. Consider the probability random variable t sub x exceeds a constant 10. Notate as capital S with 10 around parentheses. This notation doesn't include the random variable. In the probability exam, the random variable often was x. Then we write the random variable as a subscript after s. But our random variable is t sub x, so replace x with t sub x. Unfortunately, this creates a subscript within a subscript, which is difficult to read. So return to the normal subscript x, but remember it refers to random variable t sub x, not random variable x. Don't forget, age x is not a random variable. Our random variable is age x's time until death. Don't let the notation confuse the simple concept. Age x's survival function, evaluated at time 10, is the probability you will survive at least 10 years, given you're currently age x. If we change 10 to 20, it's the probability you survive at least 20 years. We can make it generic and replace 20 with t. Notice this is lowercase t, not a random variable. Lowercase t is a constant that represents a positive time t. Using generic t, the survival function is the probability that the time to death for a person age x exceeds t. Surviving t years means you do not die in t years. This is also asking what is the probability you live to at least age x plus t. Notice we assume you're alive at age x, so the survival function is based on you being alive or conditioned on you being alive at age x. Thus, we can also write it as a conditional probability. Assume you're still age x and alive at age x, but let's evaluate based on when you were born, or age 0. At age 0, your time till death random variable is t sub 0. we still want the probability to use 5 t years from x, which means surviving to age x plus t. That means we want the probability t sub 0 exceeds x plus t. Notice this captures the correct age we want to survive to, age x plus t. Since we assume you survived age x, add the conditional requirement that t sub 0 must exceed x. Now we've rewritten the survival function for age x surviving t years as a conditional probability. Since we wrote this as a conditional probability, use the conditional techniques from probability. Recall the probability A given B equals the probability A and B divided by B's probability. What is A and B here? A can be the probability t sub 0 exceeds x plus t. B can be the probability t sub 0 exceeds x. Consider A intersect B, or A and B's probability. Notice B is a subset of A. In other words, if a newborn survives x plus t years, they certainly survive x years, since t is positive. So the conditional probability simplifies to A's probability divided by B's probability, which is the probability t sub 0 survives x plus t years divided by the probability t sub 0 survives x years. Using the survival function for human lives should be intuitive. Simply think of the survival function as the probability surviving t more years given you're currently age x.